When you gaze at that fiery orb sinking into the sea, you are engaging with a cosmic illusion of breathtaking scale. The sun you see is already gone. Thanks to the finite speed of light, the sunlight reaching your eyes departed from the sun's surface about 8 minutes and 20 seconds ago. But the deception runs even deeper. Due to atmospheric refraction, the bending of light as it enters Earth's dense atmosphere from space, the sun is actually physically below the horizon when you perceive it to be just touching the water. This bending lifts the solar image by about half a degree, which is roughly the sun's own apparent diameter. This means you are saying goodbye to a ghost, a celestial mirage granted a few precious extra minutes of visibility by our planet's gaseous shell. Now consider the color. The intense orange and red hues are not the sun's true color, but a result of a process called Rayleigh scattering. Sunlight is white, a mixture of all visible colors, each with a different wavelength. During the day, with the sun high, its light takes a relatively short path through the atmosphere. The shorter blue and violet wavelengths scatter wildly in all directions, painting our daytime sky blue. But at sunset, the light must travel through a much thicker slice of atmosphere to reach your eyes. This extended journey acts as a filter. The shorter blue and violet light gets scattered away completely, often towards the eastern sky, which is why you sometimes see a subtle blue or pink glow opposite the sunset. What remains, stubbornly pushing through hundreds of miles of air, dust, and molecules, are the longer wavelengths, yellows, oranges, and reds. The intensity of these colors is not a constant. It is a direct report on the state of Earth's atmosphere. A deep, fiery red sunset often indicates high concentrations of aerosols, tiny particles suspended in the air. These can be natural, like dust from a distant desert storm, or salt crystals lifted from ocean waves, or human-made, like pollution from industrial activity, or even the aftermath of a large volcanic eruption, which can fill the stratosphere with sulfate particles that scatter light into spectacular crimson and purple displays. The famous pilot's glory, or the vivid post-eruption sunsets, witnessed globally after events like Krakatoa in 1883, or Pinatubo in 1991, are extreme examples of this principle. The clouds themselves, those canvases of flame, are active participants. Low-level cumulus or stratocumulus clouds are particularly effective sunset reflectors because their water droplets are efficient at scattering the remaining long-wavelength light. A cloud's underside, which might appear gray during the day, can ignite because it is now receiving and reflecting this horizontally traveling reddened light from the sun below the observer's horizon. The cloud's texture, whether it appears smooth, choppy, or fibrous, depends on its type and altitude, telling a story about atmospheric stability and moisture content. Furthermore, the concept of the green flash, a rare optical phenomenon occurring just as the sun disappears, is a real and scientifically explained event caused by atmospheric dispersion, acting like a weak prism to separate the last sliver of sunlight into colors, with green, and sometimes blue lingering for a second or two. Every detail you see is a clue. The clarity of the sun's disk, is it crisp or smudged? A crisp disk suggests clean, stable air, while a smudged, watery-looking sun indicates humidity or haze in the lower atmosphere, affecting the light's path. So before we even consider the ocean's role, the sky is already narrating a complex tale of astronomical geometry, atmospheric chemistry, and global weather patterns, all converging to create that singular moment of orange fire you thought was simple beauty. This is the foundation, recognizing that the sunset is not a painting, but a dynamic, data-rich broadcast from the edge of our world. Now, shift your gaze from the sky to the interface where that sky meets the earth, the coastline, and the ocean. This is not a passive backdrop, it is an active stage that shapes, amplifies, and complicates the sunset you experience. The ocean surface is a vast, undulating mirror, but its reflectivity, its albedo changes dramatically with angle and wave state. During the sunset, the water surface can transform into a path of molten gold, a phenomenon known as a glitter path or sun pillar on water. This occurs when the water is relatively calm, and the waves act as a collection of tiny individual mirrors, each reflecting the direct image of the sun. The roughness of the sea, determined by local winds and distant swells, dictates the texture of this light path. A calm sea creates a sharp, cohesive pillar of light, while a choppy sea shatters it into a billion sparkling fragments. The color of this reflected light is also filtered twice, once through the atmosphere on its way down, and minimally again as it reflects off the water, which can absorb some wavelengths more than others. But the ocean's role is far more profound than mere reflection. It is a massive thermal regulator. The temperature difference between the land and the sea, especially on a day that has seen warm sunshine, creates local wind-patterned sea breezes during the day that often reverse or settle at dusk. This shift in wind can influence cloud formation right at the coast. You might see a bank of clouds, like stratocumulus, held just offshore by an onshore breeze, perfectly positioned to catch the setting sun from underneath, creating that dramatic underlighting effect. Furthermore, the ocean exhales. Through processes like bubble bursting and wave action, it loads the lowest layer of the atmosphere, the marine boundary layer, with salt aerosols and moisture. These particles become additional scattering agents for the sunset light, often enriching the palette with more intense oranges and reds compared to a sunset viewed over dry land. The coastline's topography is a critical director. Viewing a sunset from a high cliff offers a vast, unobstructed vista and a longer sightline through the colorful atmospheric layer, potentially intensifying hues. Watching from a beach at sea level introduces elements like foreground silhouettes, rocks, piers, dunes that add depth and scale, framing the celestial event in an earthly context. The sound of the waves, the smell of the salt air, and the feel of the sand are multisensory inputs that your brain integrates with the visual spectacle, making a coastal sunset feel fundamentally different from a mountain or desert sunset. The very timing of the sunset is minutely altered by your coastal altitude. The dip of the sun below the astronomical horizon is calculated for a theoretical observer at sea level. If you are on a beach, you are essentially at that level. But if you are on a cliff, your horizon line is slightly lower, meaning you will see the sunset a fraction of a minute later. Conversely, if you are in a boat, your horizon lower further, granting you a few extra seconds of the sun's disk. This is a tangible, physical manifestation of the curvature of the Earth that you can witness in real time. The ocean also contributes to atmospheric stability. Warm air over cool water, a common coastal evening scenario, can create a temperature inversional layer, where air temperature increases with height, acting as a lid. This inversion can trap aerosols and moisture in a shallow layer, further enhancing color saturation near the horizon. It can also lead to distinctive cloud formations like the Kelvin-Helmholtz wave cloud, which, if present at sunset, can be sculpted into spectacular, glowing shapes. Even the biological activity in the water can play a part. A phytoplankton bloom, invisible to the naked eye from shore, can change the ocean's color subtly, affecting the overall color harmony of the scene. The coast is a dynamic, living platform where terrestrial, maritime, and atmospheric systems collide, and the sunset is the grand light show that illuminates this collision in real time, with every wave crash and shifting breeze leaving its imprint on the light. Having established the cosmic and terrestrial stages, we must now introduce the most important component of all: you, the observer. Human perception is not a perfect camera. It is a deeply subjective, biologically and psychologically constructed experience. The stunning orange clouds you see are a collaboration between physics and neurology. Our eyes have two types of photoreceptor cells: cones for color vision in bright light and rods for monochrome vision in low light. During the brilliant daylight, our cone cells, sensitive to red, green, and blue wavelengths, are dominant. As light levels fall at sunset, the cones become less effective, and our rod cells, which are more sensitive to blue-green light but cannot distinguish color, start to take over. This transition is called the Purkinje shift. However, our brain works tirelessly to maintain color constancy. It knows the sun is supposed to be white or yellow, so it compensates for the increasing dominance of long red wavelengths, sometimes making the reds and oranges appear subjectively richer and more profound than a camera might capture. This is why a sunset often feels more vivid in person than in photographs. Your brain is actively enhancing the experience. Furthermore, the afterimage effect plays a role. Staring at the bright, colored disk of the sun, and then looking away at the clouds, can create complementary colored afterimages, like seeing a blue spot after looking at orange, adding subtle, transient hues to the scene that are purely internal creations. Our emotional and psychological state also color filters the view. The sunset is a powerful cultural and symbolic touchstone associated with endings, peace, romance, and melancholy. This emotional priming can direct our attention, making us focus on the fiery aspects that match an internal narrative. But beyond individual perception, there is a fascinating scientific field called sky quality measurement. Scientists and amateur astronomers use devices like spectrophotometers to quantify sky brightness and color. What you perceive as a deep orange can be correlated to specific measurements of aerosol optical depth, AOD, and the concentration of particulate matter, PM2.5, PM10. In many ways, your qualitative assessment of a sunset's brilliance is a crude, biological measure of air quality. A stunningly red sunset can, paradoxically, be an indicator of poor air quality, a beautiful side effect of a polluted atmosphere. This leads us to the original data point: not all sunsets are created equal. By analyzing decades of satellite and ground-based aerosol data, researchers can trace the origin of particularly vivid sunset periods. For instance, a study might link a week of spectacular sunsets on the California coast to winds carrying dust from the Gobi Desert across the Pacific. Your experience is connected to global weather systems. The human element also includes the phenomenon of twilight. Sunset is just the beginning. Civil twilight, when the sun is 0 to 6 degrees below the horizon, is followed by nautical, 6 to 12 degrees, and astronomical twilight, 12 to 18 degrees. During these phases, the indirect illumination of the upper atmosphere creates a gradient of colors from orange near the horizon to deep blues and purples overhead. The duration of twilight depends on your latitude. It's longer at higher latitude, leading to the long, drawn-out sunsets of places like Scandinavia. At the coast, this extended twilight is reflected in the slowly darkening water, offering a prolonged, evolving spectacle. Your location on the planet, the season, and even the specific alignment of the coastline all tailor the sunset uniquely for you. This moment is a singular intersection of universal physical laws and intensely personal biological perception. You are not just watching a sunset. You are a sensor in the environment, interpreting a vast array of data through the unique lens of your consciousness, shaped by millions of years of evolution to find meaning and awe in the changing light. Let's synthesize this knowledge into a practical, predictive framework. Can you forecast a good sunset? Absolutely. While there's always an element of chance, certain meteorological conditions dramatically increase the odds of a legendary coastal sunset. First, you need high-level clouds to catch the light. The most reliable performers are mid-level altocumulus and high-level cirrus clouds. They are thin enough to be illuminated by the sun well after it is set for you on the ground, but thick enough to glow brilliantly. A sky that is completely clear may give you a beautiful, clean sunset, but lacks the dramatic cloud canvases. Conversely, a completely overcast sky blocks the show. The ideal is a sky that is about 30 to 70% covered with broken clouds at various altitudes. Second, You need a clean lower atmosphere for the sun's light to travel through to reach those clouds. This seems counterintuitive. Didn't we say aerosols enhance color? They do, but there's a balance. Too many aerosols, like thick smog or dense smoke, can obscure the sun completely, turning it into a dull, red ball that vanishes into a murky haze without illuminating the sky. You want a moderate amount of particles, often provided by natural sources like distant wildfires or dust, coupled with clean, dry air in the immediate viewing path. This is why sunsets are often most spectacular the day after a rainstorm. The rain has scrubbed the local atmosphere of large pollution particles, leaving behind smaller, more efficient scattering agents and creating crystal clear visibility. Third, consider wind and stability. A gentle breeze is better than stagnant air, as it mixes the atmosphere and prevents a dull, homogeneous haze from forming. It also shapes the clouds into interesting forms. However, a very strong wind can shear clouds apart too quickly. Atmospheric stability, as mentioned, helps trap particles in a layer, intensifying the horizon colors. You can use weather maps and apps to check parameters. Look for a rising barometric pressure trend, often indicating clearing skies, moderate humidity, and the presence of high-pressure systems, which typically bring cleaner, more stable air. Now, apply this to the coast. Check the wind direction. An onshore breeze blowing from sea to land in the afternoon can push moisture and associated clouds inland, setting them up perfectly for a sunset viewed from the shore. If you have a webcam or surf report, you can often see this cloud bank forming. Also, consider tidal stages. A high tide might bring the water right up to your feet, simplifying the foreground, while a low tide can expose reflective wet sand flats, creating a secondary mirror that doubles the sunset's glory. The phase of the moon is another advanced factor. A waxing crescent moon, visible in the twilight sky after sunset, can add a celestial companion to the scene, while a full moon rising opposite the sunset in the east can create a phenomenon called the counterglow, illuminating the landscape with a soft, bluish light. Armed with this knowledge, you move from hoping for a good sunset to strategically planning for one. You become a hunter of light, reading weather models, satellite loops, and aerosol forecasts. You learn that the most intense colors often occur in the minutes after the sun has disappeared, as the last rays illuminate the underside of higher clouds. You understand that patience is key as the show continues to evolve for up to an hour. This predictive approach demystifies the magic, but, paradoxically, deepens the awe. You are no longer a lucky bystander. You are an informed participant, understanding the why behind every shift in hue and every burst of cloud-borne flame. So what have we truly witnessed in this deep dive? We started with a cosmic illusion, a sun already set, its light bent and filtered. We explored a dynamic atmospheric laboratory where molecules and particles perform a scattering ballet to paint the sky. We saw how the active stage of the ocean and coast reflects, shapes, and frames this light. We acknowledged our own role as perceivers, where biology and psychology color the data. Finally, we learned to read the sky's own clues to predict its most magnificent displays. This journey transforms a simple, beautiful moment into a rich, multi-dimensional experience. Every fiery orange cloud is now a diagnostic tool telling you about air quality, wind patterns, and global dust transport. The glitter path on the water speaks of sea state and angle. The duration of twilight hints at your latitude on this spinning planet. The coastal sunset is no longer just a view. It is a real-time lecture in physics, geography, meteorology, and biology. It is a connection to the vast scale of our solar system and the intimate scale of human feeling. It reminds us that we live on a thin, vibrant skin between rock and void, an atmosphere that is not empty but full of drama and light. The next time you find yourself on a coast as day turns to night, you will see with new eyes. You will track the sun's descent and know its true position. You will analyze the cloud types and guess their potential. You will feel the wind and understand its role in the spectacle. You will appreciate the long journey of each photon of orange light. This knowledge doesn't spoil the mystery. It builds a richer, more resilient all-one based on understanding rather than ignorance. It makes you a citizen scientist of beauty, equipped to appreciate one of nature's most common yet profoundly complex wonders. You become part of a tradition of observers, from ancient navigators, using sunsets to predict weather to modern physicists, quantifying sky glow. This is the ultimate gift, to see the deep structure of the world while still being swept away by its beauty. It is the fusion of knowledge and wonder, and it is available to anyone who chooses to look closely, to ask why, and to seek the data behind the drama. The sunset is a daily miracle, but its true magic is unlocked, not by just watching, but by understanding. If this journey from a simple fiery sky to a universe of interconnected data resonated with you, then you cannot let the exploration stop here. This video is merely the first chapter. I have dedicated countless hours to researching, compiling original data sets, and creating visual guides that break down these concepts even further, like detailed infographics on Rayleigh scattering, tutorials on using weather apps to predict sunsets, and deep dives into historical sunsets after major volcanic events. This content is ready for you, but it only exists if this community supports it. So here is your direct mission. First, smash that like button right now. It's the single biggest signal to YouTube that this in-depth, research-heavy content is valuable and should be shared. Second, subscribe and hit the notification bell. I am not just creating entertainment. I am building a library of understanding. And as a subscriber, you will get immediate access to every new piece of that library. Third, comment below. Tell me about the most incredible coastal sunset you've ever seen and where you saw it. Your experiences become data points for all of us. And finally, share this video. Share it with a friend who loves the ocean, with a science teacher, with anyone who has ever paused to watch the day end. Let's build a community of curious observers who see the world not just for what it is, but for the incredible processes that make it so. The next sunset is coming. Will you just see it, or will you understand it? The choice and the tools are now yours. Take action.